Okay. All right. So let's look at it. Okay, so if you look at this one, we have a resistor in between Vn and Vo. So we've got this resistor here in between Vn and Vo. So that's the same. We do have a resistor after Vo, but that's not a problem. That's just something to add in later. And Vn on our example for an inverting circuit just says Vn, doesn't say where the voltage is coming from. And what we have here is a current source with a resistor in parallel. Well, we can very easily change that into a voltage source using source transformation, and I prefer a source transformation anyway. So, I mean a voltage source anyway. So I'm going to change that to a voltage source, and the voltage source will be IS times RS. I'll just write it that way, IS, RS. And then we'll still have RS, we still have that resistor. And VP goes to ground. And from here, I have that. And this is RL. And this is RF. And IL is in the expression we're looking for. We're looking for IL over IS.
I thought IL's past that little thing coming out of the output of that triangle.
It is. Yes, it is.
Like
It is. No, it matters. The op amp, the little, yeah. It is. No, it matters. It matters because, yeah. Yeah. Okay. Okay, so if we now compare this to our model inverting circuit over here, we can see what the relationships are. We can see that RS is like our R1. Vn is ISRS. RF is like R2. And our V out is right here. It's before the current and RL. So we have that from our example that A equals minus R2 over R1. What that means is that VO equals minus R2 over R1 Vn. That's what that A is the gain. So it's showing what you would multiply Vn by to get V out. So now we can just transfer that with using our values over here. So VO equals R2 was like our RF, so minus RF. R1 was like our RS. And Vn is ISRS. And now you can see that the RS's will cancel, and I get that VO equals minus RFIS.
Wait, so what's the A equals mean on that?
This is the gain. So what that means is anytime you see that, it's sometimes given as capital G. Your book gives it as capital G. I got this from the notes from your class. Her PowerPoint had A. So ordinarily, you would say that V out equals A times V in. And so this is the number that you multiply the voltage source in by to get the voltage source out. Okay. I also know if I look at my IL current over here, and so I'm just going to look right here, see how I have this labeled as VO? So the voltage right here is VO. The voltage here, of course, is ground. That's ground. And so IL equals VO minus 0 over RL, or VO equals ILRL. Well, now I have that VO equals ILRL. I also have that VO equals minus RFIS. So I can say that ILRL equals minus RFIS. And I'm looking for, the problem is asking me for IL over IS. So divide both sides by IS and divide both sides by RL. And I get IL over IS equals minus RF over RL, which is what I was supposed to get. And then part B says if RL equals 12 kiloohms, choose RF such that GI equals negative 15.
Wait, so that IL over IS, just that recent thing you wrote, that's what the answer is for part A?
Yes,
That's what it's
for part A. Now, RF equals question mark, so we want G to be negative 15. GI. So GI is IL over IS. That's defined for us in the problem. So IL over IS, we want that to equal negative 15. Well, we know that IL over IS is minus RF over RL. So I can do minus RF over RL equals minus 15, and RL is 12, so minus RF over 12 kiloohms equals minus 15, or RF equals 180 ohms. And I forgot this when normally I cut and paste to OneNote the problems, but today I used Word and just had it print page at a time to OneNote, and I forgot, it always just prints the page twice.
So do you have to change the kilo to the times do the kilo to ohms?
I do. That should be kiloohms. Thank you. Okay, so last time we looked at an inverting op amp. So this time I'm going to go ahead and ruin the surprise and tell you that we're working on a non-inverting op amp. And let's see how we can see that. So let's go back to our picture of a non-inverting amplifier. Okay, so we can see that we have the two resistors coming out of the op amp, and between the two resistors we have the feedback going into the negative, into Vn. And we have that over here too, so we've got that. And then what's outside of Vout, well, that's not part of the op amp really, so we can just deal with that when we get to it. So we can see that we have this part matches up, and then Vn is just a voltage in. And so if we can figure out what Vs prime is, what that voltage in is, then that's going to be the same as our Vn. So even though we've got this other stuff here, if you just know what that voltage is, and you know what these two resistors are, then you can see it matches up just like with the non-inverting amplifier. So we can say that Vs prime is equivalent to Vn, and that 70 kiloohms is like R2, and 10 kiloohms is like R1. And using this A for our gain, that means that Vout equals 1 plus R2 over R1 Vn, or Vout equals 1 plus 70 kiloohms over 10 kiloohms times Vn, which is Vs prime. Okay, so now let's take a look at Vs prime. If you look at it the right way, you can see that we can use voltage division on it. Because if you take this part of the wire and just kind of like unbend it and stretch it that way, what you've got is a wire that looks like that goes from ground to Vs, and the point we're looking for, Vs prime, is right there in the middle. And this bottom one right here, that goes with this one. That's 20 kiloohms. The top one is 5 kiloohms. So we can use voltage division here and say that Vs prime equals Vs times 20 kiloohms over 25 kiloohms. Which is 0.8 Vs. Okay, so now we can go back over to the expression we wrote over here on the side and say Vout equals, and then 1 plus, well, 70 kiloohms over 10 kiloohms is 7, plus 1 plus 7, which is 8. It's 8 Vs prime. So Vout is 8 times 0.8 Vs, our Vout equals 6.4 Vs. Okay, so now we are looking for our total gain. Our total gain is VL over Vs. Right now we have Vout. So we have the voltage right here. We want VL. So we are looking for the voltage right here. Well, once again, we can do current division. So, not current division, voltage division. So right here, that's V out, which was 0.8 Vs. This is 70K. This is 10K. This is ground. And VL is the point in the middle. So I just went up and over to here. So it's just that part right there. So VL equals 0.8 Vs times 10K over the sum of those, which is 80K. Our VL equals 3.2 Vs. And we're looking for G, which was VL over Vs. VL is 3.2 Vs, and Vs is Vs. So that's 3.2, so that's our gain. Okay, the linear range, and again, I'm not sure you need to know this, but it's easy, so I'll go ahead and show you if you've done the rest of the problem. So linear range says that the absolute value of VO has to be less than or equal to VCC. VCC is the voltage that is the op amp is plugged into. Yeah, that's the voltage that it's plugged into. It'd be given to you in the problem. So VCC here is 6. V out, we found was 0.64 Vs, or 6.4 Vs. So the absolute value of 6.4 Vs has to be less than or equal to VCC, or which was 6. And this means that negative 6 has to be less than or equal to 6.4 Vs, which is less than or equal to 6. And then divide all three sides by 6.4. And you get negative 0.9375 is less than or equal to Vs is less than or equal to 0.9375. Did you have a chance to sign in the email that I sent? Okay. Yes.
I don't know if what I'm gonna say is right, but isn't, since the absolute value is on V naught, wouldn't that be the plus or minus? Or no, is that wrong?
No,
No.
no, it's not. Yeah, that's it's a yeah. It seems like it would be, but yeah. It kind of is if you set it up a different way, but this is just the shortcut way of making it work. If you take what's in the absolute values and you put the plus or minus on either side of it. That's if it's a less than. Okay, other questions? Yes. Too far or? Okay. You ready? Or still looking?
I'm still processing.
Okay, all right. Let me know.
Thank you.
Okay, so I copied my notes wrong. And this is Vs prime is 0.8 Vs. So that's that part. And then I accidentally copied that from here when I should have had here 6.4 Vs. But the answer here is right because I used the right numbers when I did the calculations. But yes, thank you for catching that.
That's what I was.
We're going to do one that we're not trying to match it up with one of the other op amps. We're just going to use our rules for op amps to figure it out. So our rules tell us that VP equals VN and IP equals IN equals 0. You might also see these listed as V plus equals V minus, or I plus equals I minus equals 0. Which ones do y'all use?
I think the V plus equals.
The plus and minus?
Yeah.
The plus and minus? Okay, I'll try to remember to use that.
V plus.
Okay, but do be aware, you will see these guys again in electronics and in other places, and they can, they're, you'll use either notation. Okay, so we can see very easily that VP has to be 5. Well, once we know that VN has to be 5. So the voltage right here has to be 5. If you know me, I really don't like current sources. I'm going to redraw this to be a voltage source. 2 times 2 is, is that supposed to be 2 amps or 2 kiloamps? I mean, 2. I suspect this was supposed to be 2 milliamps. I'm going to change it to 2 milliamps. And then that makes this 4 volts. And then this is 2 kiloohms. Six kiloohms. That's 4 kiloohms. 6 kiloohms. And V out. Okay, so I know the voltage right here is 5 volts, so I know that. So I am going to call the voltage right here V, and the voltage right here is V out. So I am going to start with V, and I'm going to write some node voltage equations. I'll start by going down. So V minus 4 over 2K plus, and now I'll go to the right. V minus 5 over 6K. And then I will go up and around. So this is VO, this is VO, this is VO, that's VO. V minus VO over 4K equals 0.
What's the case?
Kilo?
Oh, kilo. Oh,
Yeah.
Oh, you never write them.
I never write the ohm. Well, I do like in the diagram, but when I'm putting it into the equation, I'm just treating it as a number, and the K is easier for me than writing 3 zeros. So it's just being lazy. Besides, they're all going to cancel. I can cancel them right now. By K's. Multiply through by 1,000. Okay, and then starting from the 5 volts, I would have 5 minus V over 6K plus, and then going up, V minus V out over 6K equals 0. And again, on this one, I can multiply through by 6,000 and get rid of all of them. So on that bottom equation, this should have been a 5, not a V. I get minus V naught equals minus 10. That's my bottom equation. On my top equation, if I multiply through by 12, then I'd get a 6V, a 2V, and a 3V, which would make 11V. I would get a minus 3V naught, and I would get a negative 24, which would come to the other side as a 24, and a negative 10, which would come to the other side as a plus 10. So I'll multiply the top equation through by negative 3, and I get 3V plus 3V naught equals 30, and then 11V minus 3V naught equals 34. Add my two equations together. 14V equals 64. V equals 32 over 7, which is something. And then if I plug back into here, minus 32 over 7 minus V naught equals negative 10 ends up with, or this is V out, ends up with V out equaling 5.429 volts, which I think was the goal of the problem. Yes. This one right here was the node voltage equation coming out of V, and I multiplied through by 12 to get rid of the denominators, so each of these got multiplied.
I see. Okay, yeah, I see.
Okay.